Today in Lab 4, we will be observing complex oscillations and attempting to model these movements using Newton's second law and the energy principle. We will be using Newton's second law and equations derived from it to predict the motion of the mass, and the energy principle will be used to analyze the results of the motion. We found that the model was accurate in predicting the motion of the mass. We also found that the energy of the system was conserved, and that there is no work done on the system during the observation period. There will be two interpretations of the system for this lab. When using Newton's second law, the system will be interpreted as only the mass. When using the energy principle, the mass, the spring, and the earth will all make up the system. After analyzing the motion and tracker, it can be seen that the object is oscillating in both the x and y direction. From this, we can derive some initial conditions and constants from needed for the model. The spring constant was found by using this equation and inputting the oscillation period for the y direction. L naught was found from Newton's second law when the mass is left at rest. Here is a Python code used for the model. First, we input the initial conditions and constants. Then, we must set the length and direction of the spring. These equations here are calculating the different energies of the system using the equation shown earlier. Next, we must calculate the net force acting on the object. We then input the velocity and position update formulas to predict the motion of the object. In this section, we update the springs information, and here we update the energies. A change in energy is calculated by subtracting the final energy from the initial energy. The model's predictions were mostly accurate to what really happened. For both directions, the magnitude isn't as high as the observed magnitude, but this could be due to our neglection of drag forces or poor motion tracking. In the x direction, the period of oscillation is slightly offset, but this could be due to the fact that we calculated the spring constant k using the y direction's motion period of oscillation. A possible solution to this would be to calculate two spring constants because the y direction has a higher frequency than the x direction. Next, we can see if the energy of the system was conserved by looking at this graph here. We see that the gravitational potential energy oscillates with the spring potential energy, which makes sense. If the spring is stretched, it's lowered to the ground. The kinetic energy also oscillates during the period. Throughout the whole period, the total change in energy appears to be zero, so there's no work being done on the system. That's about it. See ya.